Hi, I'm Jithin Govind from Kerala. I have a bachelor's in physics from the University of Calicut. I have a master's in physics from Christ University, Bangalore. And I'm currently pursuing my second post graduation in nanoelectronics and nanoengineering from Amrita School of Nanosciences and Molecular Medicine, Kochi. So, as far as teaching experience is concerned, I haven't really, taught in a professional level platform like Vedantu, but I do have decent experience tutoring my friends and some kids in the local institutions. Apart from that, I don't have a professional experience as in that sense. So this will be my first try, tutoring in online sessions, and I am grateful that Vedantu is giving me a chance to try it out for the application. So for the trial, I will be teaching photoelectric effect, which is a very important topic in the 12th grade NCRT books, and I will be sourcing it from the NCRT book itself. So I don't have any extra sources, and I was instructed to use a stylus to teach, but uh, at the moment I don't have it. So I'll be making a PowerPoint presentation and I'll be teaching from the same. So let's see how it goes. And once again, thank you, Vedantu, for giving me this opportunity to try it out. Thank you. Hi everyone, and welcome to my mini demo class on photoelectric effect. So this is a very demo class on this one particular topic that is very important in terms of class 12 physics, especially in the NCRT syllabus. And I don't have a like pen stylus support for now, so I'll be just relying on a PowerPoint to teach this topic. So without any further ado, I'll just jump directly into the topic now. So, if you want to talk about the brief history about photoelectric effect, we have to start from Heinrich Hertz, who in the year of 1887 discovered that there is some kind of emission when he conducted some experiments regarding UV light and metal surface interaction. So, basically, what he observed is that whenever there is a UV light incident on a metal surface, especially on the surface of a metal, there is some kind of emission of charged particles from here. So this is the very first observation of photoelectric effect. And in the following year, William Hallwachs actually observed the same effect again. But what he noticed is that whenever the UV light is interacting with a zinc plate, zinc is a metal, okay. So whenever UV light is interacting with zinc plate, it can either lose or gain charge. So this suggested that there is some kind of charged particle emission, which was later then found to be electron emission. And in the year of 1899, it was Philip Leonard who actually conducted the experiment, like the setup that we are gonna show in the next slide, and where he actually shined a UV light onto a metal plate, which led to rejection of electrons in the vacuum tubes, producing a measurable current. So basically, he's the one who measured the photocurrent properly, and which led to the further research and investigation about the photoelectric conductivity and all. So all these three guys were the actual trio behind the photoelectric effect. But even then, it was only Albert Einstein who can actually explain how this effect come into practice. So what actually caused the photoelectric effect? This was explained by Mr. Albert Einstein. Okay, so here in this slide, I'll be briefly outlining the experimental setup that Philip Leonard used to explain the photoelectric effect, like the experimental findings and all. So in this setup, the most important part is the evacuation tube. Okay, this vacuum chamber is very important because we don't need the electrons which are emitted from the metal surface here to be interacting with all the gas particles around it. So we are evacuating that tube. So we have a very free pathway for the electrons to reach from plate C to plate A. So plate C and plate A are actually metallic plates. The C is called emitter plate because this is where the light will be coming and interacting and producing like emission and all. And A is called the collector plate. Okay, now the plates C and A are actually kept at a potential difference, which is basically supplied by the battery. So battery is actually the voltage generator here, and this voltage is measured using a voltmeter. We have a microammeter to measure the current generated by the photoelectric effect. Okay, and the commutator is basically a device to switch the polarity between C and A. That is, we usually tend to take the measurement with A, the plate A being positive potential than plate C, but we also want to switch to the negative side. That is, we have to make A more negative than plate C. And also we need to understand that the source that we use is actually either a UV or any monochromatic light is also possible. We tend to stick with UV for now. So this source has to be monochromatic. So only one wavelength is preferred if you want to, practically learn more about photoelectric effect. And the quartz window is used to like direct this light onto the metal plate. Okay. So this is the experimental setup overall, and the thing is that the photocurrent varies with the light intensity I, frequency and voltage, and the work function phi. So intensity is of the light, the frequency is also of the light source, and the voltage V is actually what we supply here. And the work function is actually an interesting quantity because it is typically referred as the minimum energy required to emit an electron from the metal surface. So it's like the minimum energy that the photon has to give to emit an electron from the metal surface so that it can be attracted to the plate A. So when you have a positive potential here at plate A, the electrons are attracted towards to the plate A, which will collect the electrons and hence conduct the photocurrent. Okay, so if you have a negative potential at the plate A, will gradually repel away all the electrons. Okay, this is also very important. Now this is like how the experiment was conducted and many data has been collected. So in the next slides, I'll be explaining what exactly were the findings of the photoelectric effect experiment. Okay. Okay, now since we have familiarized ourselves with the experimental setup of the photoelectric effect, let's now look into some experimental findings or the data related to photoelectric effect. So one of the key observations that Leonard undertook was that the photoelectric current that we measure is actually a function of intensity of the incident radiation. That is, the more intense your light or the more bright your source is, the photoelectric current will also increase linearly with that. This won't go forever. Okay, so at some point it will saturate like a horizontal line like this, but typically the brighter your source is, the more the photoelectric current will be generated. Okay, so this is one of the critical observations. So this actually makes sense if you consider light like a particle picture. Like the more the number of photons that are being incident on the metal plate, the more is the photoelectric current generation, which means it will linearly increase with respect to intensity of light. So that's how the first plot was explained. Now, if you look at the second plot, we have the potential between the plate C and A in the x-axis, and on the y-axis we have the photocurrent. So here I1, I2 and I3 refer to intensity of the radiation. So I3 is being more intense radiation, I2 moderate intensity, and I1 is the least intensity radiation. Okay. Here the critical point is that for all these three intensity, the frequency of the radiation is same. Okay. So with that in mind, we can see that the minimum negative or retarding potential V0 given to plate A for which the photocurrent stops or becomes zero is called a cutoff or stopping potential. I told you that usually we take the measurement when the plate A is kept at a positive potential at this side, the right side. Okay, in the left side, we are actually inducing a negative potential to the plate A so that the current will gradually decrease because the plate is repelling away the photoelectrons, right? So eventually it will come to a point that at a particular negative potential the current will stop. That is, the plate can repel even the electrons having the maximum kinetic energy, Kmax. Okay, so why is this stopping potential important? It's important because this stopping potential, if we know that, it allows us to calculate the energy associated with the maximum kinetic energy of the electrons. So Kmax is given by E V naught. Okay, so this is a very peculiar observation. So if you make the plate negative with respect to plate C, that is the emitter plate, we can actually stop the electrons at one point, which means the current will become zero. And if we can find that retarding potential or stopping potential, we can find the kinetic energy associated with the electrons. So for a given frequency of incident radiation, the stopping potential is independent of its intensity. So I told you the I1, I2, I3 are different intensity of light. So for all these three intensities, the stopping potential was the same. Okay, so the V0 is already depending on the frequency of radiation. and the work function of the metal. I told you the work function and frequency are the key parameters here. So intensity can increase the photocurrent, however it cannot have much effect on the stopping potential or any other parameters of the photoelectric effect. So this is the key takeaways from this slide. Okay, so in the earlier plot, I told you that the stopping potential do not depend on the intensity of the radiation. However, they depends on the frequency of the radiation. So here they have plotted the photoelectric current against the potential of the plates. Okay, so we can see that we have three different stopping potential when we use three different sources of light. That is the frequency nu1, nu2, and nu3. Where nu3 is actually the greatest frequency and nu1 is the least frequency. So at different frequencies of light, we can have different stopping potential. However, the saturation current will be the same for any frequency of the light. However, one key takeaway from this slide is that at a particular frequency, the stopping potential can also be zero. Right here, nu1 is giving a stopping potential of minus V01. However, this is very close to the origin, that is zero, right? So at a lower frequency than this, we can also expect stopping potential to be zero. Okay, that particular frequency is called threshold frequency. Okay, this minimum cutoff frequency nu naught is called the threshold frequency, and it's a function of the material that you use. For different metals, the cutoff frequency will be different, or the threshold frequency will be different. So some key takeaways from this is that if you look at the plot here also, they have plotted stopping potential V0 against the frequency of incident radiation for different materials, metal A and metal B. So V0 varies linearly with the frequency. If you look at metal A, the V0 varies linearly with respect to increasing frequency. Also true for metal B, where the V0 is again varying linearly with respect to frequency of radiation, right? So both the metals interestingly have two different cutoff frequencies. So that's why I told the cutoff frequency or threshold frequency is actually a function of the material we use. Depends on the material. If I use a copper, I'll get a different cutoff frequency. If I use zinc, I'll get a different cutoff frequency. That's the key point here. Okay, so the cutoff frequency was a very interesting result of the photoelectric effect experiment. And also, if you look at this plot, we can see something called the saturation current. So saturation current is the maximum photocurrent when all the emitted photoelectrons are collected. The electrons are not an infinite source of charges, right? So there will be, for a particular material, there will be a finite number of electrons. So if you increase the voltage further and further, you won't get an infinite increase in current. You will finally saturate at some point, and this current is called saturation current. Okay, so that's all from this slide. Okay, so that was all about the experimental findings of the photoelectric effect. Now we need to correlate with the theory available, right? So at the point of time when they were first discussing photoelectric effect and using experiment to verify their theories, the major theory that explained the behavior of light matter interaction was the wave theory of photoelectric effect here. So wave theory was very successful in explaining interference, diffraction, polarization, etc., using the retromantic wave concepts and all. But in terms of photoelectric effect, it has certain kind of predictions, but do they really agree with what we observe from the observations, right? So let's see that. Majorly, wave theory predicted that electrons absorb the energy continuously from the radiation's electric and magnetic field. Is it true? We now know that it's not true, because this can lead to kind of little bizarre predictions, because it expects that the kinetic energy of the photoelectrons will increase with the intensity of the light. If it's a continuous absorption of energy, the more intense your light is, the more the number of photoelectrons kinetic energy will also become, right? We see that even though the number of photoelectrons are increasing with the intensity of light, the kinetic energy is not a function of intensity of the light. So it only depends upon the frequency of light we used as well as the work function of the material. So this was false. So the statement was already in trouble. And also it predicted there is no threshold frequency. According to this concept, if the electrons absorb energy continuously, even for any intensity of light, no matter how faint it is, for any frequency of light, there will be emission of photons, right? Okay, is it true? No, because we saw that there is something called the threshold frequency below which there is no emission. So for a particular material, there exists a frequency called the threshold frequency below which there is no emission. Okay, so this is again false. And also, according to this concept again, there will be a delayed emission of electrons from the material. Why? Because if you have a very low frequency light, electrons will gradually absorb the energy, that is continuously absorb the energy, and it will take some time for the electrons to get emitted from the metal surface. Is this true? No. Because why? We observe that the photo emission occurs instantly even with a very low light intensity. Around nanosecond delay will only be there, which cannot be saying, we can't say that there is a huge delay in electron emission even for low intensity light. So this wave theory was unsuccessful in explaining the photoelectric effect to its full capacity. And that's where Mr. Einstein came in, and he explain the photoelectric effect based on the Planck's quantum theory of light. Okay, so using that, he could successfully observe the photoelectric effect, and for this work, he was awarded the 1921 Nobel Prize in Physics. So let's see how Einstein was able to change the viewpoint and explain this photoelectric effect fully. Okay, so let's see what was the game-changing theory that Einstein used to explain the photoelectric effect. So Einstein used the quantum theory of Planck to say that light consists of discrete energy quanta or photons. That each photon has an energy of E is equal to h nu, where nu is the frequency of incident radiation in hertz. So basically, what Einstein said is that we can consider light as discrete packets of energy. Okay, so each packet is called a photon, and each photon will have a particular frequency nu, and based on the product of h and nu, we can find the energy associated with that photon. So h is called the Planck's constant. Okay, so based on this, we can say how energetic that photon is. Okay, and another one main thing that Einstein explained is that a single electron can absorb one photon in the photoelectric process. So a photon emission occurs only if the photon energy is greater than the work function phi naught. So phi naught is actually the work function here. Only if the incoming photon energy is greater than the work function can there will be emission of photon. Okay, so you can also think that what if the energy is equal to the work function? Then also the electron is excited from the ground level to the vacuum level, but still there will be not emission because there is no energy for the electron to escape from that place, right? It can only be excited to a higher level, not escape from that. So sorry, the matter. So this condition is very important, that for photo emission to occur, photon energy should be greater than the work function of the material. And based on this values, we can also estimate the kinetic energy, that is the maximum kinetic energy of the emitted electron. It is given by Ke max is equal to h nu minus phi naught. And also, Einstein explained the concept of threshold frequency below which the photo emission do not occur. So until this point, nobody has actually thought about light as photons, that is as particles. So it was Einstein who actually explained the threshold frequency below which the photo emission does not occur. And also the photoelectric current is proportional to light intensity for any frequency that is greater than the threshold frequency. So threshold frequency is very, very important. Okay, above which only photo emission will occur. So the photocurrent will be proportional to the light intensity. That is, more and more photons are actually releasing more and more electrons. So for a given material, kinetic energy of the electron depends only on the photon frequency, not on the intensity. If you look at this equation, h is a constant, Planck's constant, right? Nu is a constant for a given radiation. That is, the frequency will also be a constant, and work function is a constant for a given material. So if you change the material, work function will change, and frequency will change with respect to the radiation that we use, and h is a constant. So both frequency of the incident radiation and work function of the material is what determines the maximum kinetic energy of the emitted electron. Okay, so intensity is not the x factor here, it is more or less the frequency and the material. Okay, so that contradicted directly with the wave theory, and it was staggeringly useful in explaining how the observations matched with Einstein's predictions. Okay, so photo emission is instantaneous was also incorporated into Einstein's explanation, since the absorption of photon by an electron is an immediate process. I already told there is be like a tiny nanosecond delay in this excitation and absorption of in the electronic transitions. So Einstein was also successful in explaining this particular point. So let's just say that wave theory predicted that you know if you have a light radiation which is very low on energy, slowly the electron will be excited, which means there will be a significant time delay, which is in milliseconds or something. But this is not the case when you come to the experimental section. So what we observe is an instantaneous emission, and Einstein was successful in explaining that. Okay, that is why he was awarded the Nobel Prize. And also from Einstein's findings, we can see that stopping potential V naught can be expressed as h nu minus phi naught by E. So E is the charge of the electron, and phi naught is the work function, and nu is the frequency. So if we plot V naught, as I showed in the earlier slides, if you plot V naught against the frequency, we can see that the stopping potential is increasing as the function of frequency. So these are all explained by Einstein's theory. And then there was another scientist called Millikan who went on to do some experiments to disprove Einstein's theory. He did not believe in Einstein's theory, but what he ended up doing was that he calculated based on Einstein's concepts. He ran some experiments and he calculated Planck's constant to its accurate value, that is 6.626 into 10 to the power of minus 34 joule second. So this actually confirmed Einstein's equations and Einstein's theory was correct. So in this slide, I want you to take away that this equation, Ke max is equal to h nu minus phi naught, is called Einstein's photoelectric equation. So this explains the whole photoelectric effect more or less. So this is how Einstein was successful in explaining the photoelectric effect. Okay, so far what we have seen is that explanation of photoelectric effect in the NCERT based textbook. But to really understand how the photoelectric effect works, we need to look at the band diagrams in the metal as well as the vacuum. So if you take the case of a metal, the metal has something called a Fermi level. Okay, Fermi level is nothing but the maximum energy level an electron can occupy at absolute zero Kelvin temperature. So this is where most of the electrons will be seen. I just wanted to understand that Fermi level has a lot of electrons. Okay, so which are like loosely bound to the metal surface. Now, whenever an incident radiation is coming, it will excite these electrons to a higher level. In this case, we can call it as a vacuum energy level, EVAC. Okay, so electrons will absorb the photon from the radiation and it will get excited into the vacuum level. So this electron is actually not bound to the metal surface. But if you look at the energy level here, it doesn't have enough energy to escape this system. So what happens is that it is in a very unstable state now. So it can lose some energy, then it will come down. Like maybe it will interact with another electron or lose some energy, or maybe it is slightly perturbed from this level. So usually what happens is that whenever an electron is exactly absorbing the energy required to cross over to the vacuum level, it will just go there and come back, relax back to the ground state. Okay, so in photoelectric emission, if we want the electrons to be emitted outside the material, that's why I told you h nu should be greater than phi, the work function of the metal, right? So if you look at the energy levels, this energy difference between the vacuum level and EF, the Fermi level, is what we call as the work function of the material. So our incident energy radiation, incident radiation energy should be greater than phi. Only and only then will the electron have some energy, like spare energy, like in this region, to escape from this system. That is the only case where the electrons are successfully emitted outside the system. Okay, so this is how the whole process works, and I hope that makes it clear. And this is a band level understanding of the photoelectric effect, and it's not really necessary that you need to study for NCERT exams. I don't think so, but this is just to understand this. Okay, so far we have seen the photoelectric effect, how it was explained by Einstein using the particle picture of light. So until this point, everybody was saying that light is made of waves. So wave theory can explain how light interacts with a lot of its surroundings and all. But when it came to photoelectric effect, Compton effect and all, the wave theory was not giving accurate prediction. That is when Einstein came and said, hey, look, that radiation, when it is interacting with matter, the radiation will behave as a particle. And these particles were termed as photons. And each photon has an energy E is equal to h nu given by Planck's quantum theory. And it will have an associated momentum and a speed. Okay. And all the photons of light of a particular frequency and wavelength has the same energy and given by this equation, and momentum given by this equation. So whatever the intensity of the radiation may be. So frequency is what really matters, is what has been underlined here. Now, by increasing the intensity of light of a given lambda or frequency, there is only an increase in number of photons per second crossing a given area, with each photon having the same energy. Thus, the photon energy is independent of the intensity of the radiation. Basically saying the same thing. It's not about the intensity of radiation, it's about the frequency of radiation. Okay, and I really wish I could go in detail about this because I'm specializing in photonics, but for the scope of the discussion so far, I'm just going to limit myself here. Photons are electrically neutral and are not deflected by electric and magnetic fields. This was also a very interesting thing about photons. And whenever a photon and a particle collides, the total energy and total momentum are conserved. These are like basic laws. And number of photons may not be conserved. This is very important. Even though the energy and momentum of a photon may be conserved, the number of photons may not be conserved. Photon can be absorbed, the new photons can be created, even though the energy and momentum of the total system will be conserved. So this is what the particle picture of electromagnetic radiation tells us. So that's all about photoelectric effect from my side. So like I said, I took most of the information regarding photoelectric effect from the NCERT textbook of class 12, and I will highly recommend anyone reading about photoelectric effect to base it on NCERT textbook. And you can always read further, but it's better to go through NCERT first. And there are many problems related to photoelectric effect on that. To just keep the video short, I didn't want to include the problems. I usually do, but I didn't want to include the problems because it will just go on, and it will turn into a 1 hour class. I don't want that for a demo class. And basically, the portion is very simple, and I will highly, I really want the readers or the listeners to go ahead and see what they can learn extra about the photoelectric effect. Whenever a topic in physics comes, you need to be really, really thorough with the basics. And basics, if you're really, really strong in basics, you can topple any complicated concepts just like that. So I will take this opportunity to thank Vedantu for giving me this opportunity to apply for this job and prove my teaching merit in some ways. So I'll end with the thank you note, and I hope you understood whatever I presented in the class. Like I said, I don't have a stylus for now to actually draw and show equation. Usually I do prefer a board to present. I took multiple classes using PowerPoint, but I usually integrate board, whiteboard and all in my classrooms. But it was a good experience applying for this job, and thank you for this opportunity again. So we'll see. Thank you.